16, part 3, we're going to cover thermal properties of water. So we already discussed a little bit about water, how water has a very high specific heat capacity, and it can store large amounts of heat energy in its molecules. So this affects temperatures all around our planet. So we already talked about how on a beach, the water can be cool while the sand is hot, because the sand has a lower specific heat capacity. It's like 1/6 that of water, so it heats up 6 times faster. So the sand will heat up daily and then cool down at night often. The water kind of stays the same temperature. Doesn't heat up that much. And as you know, if you've ever gone swimming in Lake Michigan, it takes till like half the summer before the lake is warm enough to swim in comfortably for most people. Now, this also affects the winds that are available. Basically, when you live on the coast, the temperatures are more moderate. And one reason is because you get lovely breezes off the sea during the daytime. And that occurs because the hot air over the land rises up. And so cooler breezes come in off the ocean to bring in that cooler air. At night, the reverse happens. The water is releasing more heat energy as the land cools down, and so you actually, the land breeze actually switches directions, which is pretty cool. But also in a desert, deserts don't have much water, and water is a moderating influence. It slows down the change in temperature. So in deserts, you can go from you have temperatures up to 100 degrees during the day, and then at night it'll plunge back down to the 40s. Because you don't have water droplets, wrong color, you don't have water droplets hanging around moisture in the air, which we call humidity. You don't have moisture in the soil, and so it heats up and cools down much faster. Now, around the globe, our Earth is covered. 71% of the Earth is covered by water. So the high specific heat capacity makes a big difference. When you live on the coastline, you often live with moderate temperatures. I used to live in California, just above LA. And the thing is that the temperature there was pretty much 70 degrees all year round. That was Ventura, California. So because during the winter, you get warm air from the water. During the summer, the cool breezes that you get and the ocean absorbs the heat energy around you. So what happens is you get more moderate temperatures. So you get more extremes in places, again, that we were talking about that don't have much water. Now, water can transport heat energy thousands of miles. The whole ocean is filled with conveyor belts of water, these currents that circulate. One of the most famous is the Gulf Stream. And the Gulf Stream comes up from the Gulf down here of Mexico. And so it takes hot water from the Caribbean and it transports that water up the coast of Florida, up the coast of New York, New Jersey, and then it goes off to Europe and keeps Europe warm. So here we've got France and Spain and England, and they have much more moderate temperatures normally because of the Gulf Stream carrying heat energy. And so that's an extremely important current for Europe because it allows people to live in Europe at much higher latitudes than they might normally. So you can see there are all these cities high up in Europe, and those are much higher than Canada, than most cities in Canada that we consider quite cold, like Montreal, right? And Vancouver, where they have the Winter Olympics and stuff. And so London is higher than Vancouver, and Paris is about the same as Montreal. And Chicago is about the same as Madrid and Rome. But we don't think of Chicago as being those lovely warm places, those Mediterranean temperatures, right? That's because they've got water. We have a lake, but we don't have water surrounding us, and we don't have the Gulf Stream bringing temperatures up. So anyway, so you have these cities, lots of cities in Europe that are affected by that warm water. So you have a whole bunch of these cities that can survive. Whereas over here in Siberia, not so many cities, right? And here in Canada, not so much. Um, so yeah, so having those currents bring water makes a big difference. And so the ocean currents, the major ocean currents, you can see that can bring hot water or cold water. Usually if they're coming from an equator, so like we were talking about how the Gulf Stream brings warm water because it's coming up, right, from the equator, sort of. So also the beaches in Brazil are good because they get a current bringing water, warm water down the coast. You also get I've had students from South Africa. There are the good beaches on this side where the water's coming down from the coast. And then you have the places where the water's coming up from the Arctic. So the beaches are cold on one side of South Africa and warm on the other. And South America, same thing. Peru isn't known for its beaches. You get the cold Antarctic current coming up. And also, the dirty little secret for those of us who live in California is that our beaches are cold. You can see there's this cold current that comes down most times of the year. And so our beaches are cold all the way down to LA. And even there, they're fairly cold, even though you can have warm beaches up here in New Jersey because they have the Gulf Stream. So when you're planning a vacation, if you're thinking about beaches, you might look at the direction the currents are going. Okay, now we talked about how materials can expand or contract with temperature changes. But also another thing that happens is solids are usually contracted more than liquids, and liquids are usually contracted more than gases. So gases will usually have the highest volume, and solids the least. And the thing is that water has some exceptions to that rule. Water, again, is a very special material. And so that's why a solid water, ice, floats in liquid water. Whereas for most materials, the solid, like if you had some solid aluminum, it would sink to the bottom of liquid aluminum. So anyway, molten aluminum. So anyway, so yes, so ice is weird and water is odd. So let's go see why this happens. So what happens is that for water, when it starts to freeze, the ice crystals are these hexagon shapes. So the water molecules are forced into hexagons, which leaves a lot of room in the center that isn't being used by molecules. So the ice is less dense than the water. Here's the water molecules, and they can get quite close to each other. And so it's the crystal structure of the ice that makes the solid less dense. So this is why ice will float in water, because it is less dense than water. And so here's some pictures of snowflakes, which have that hexagon shape, which is showing their crystal structure, which is the hexagons. Now, there is something else that goes on with water too. While it's still liquid, even before it becomes ice. Now, this is from your book. And so let's look at this chart here. And you can see how the density, there's a water vapor, and then it becomes more dense to become a liquid. And as you decrease temperature, then the liquid gets more and more dense with a smaller volume, except when it reaches this little spot here, and then it becomes ice, the solid, and then the density shoots way up again. But let's see what happens in this little corner. So if you look at this picture, that's what's happening in that little place there. As the temperature is lowering from 18 to 16 to 12 to 8 to 4, at 4 degrees, something starts to happen. And the water starts to expand again. The volume starts to get larger again. So water is, I think, the only material with this peculiar thing that happens. And again, that's because of the ice crystals. Basically, this section here is really more like a slush. Ice crystals are starting to form, and ice crystals take up more room than water. So the water starts to expand again because it's got some ice crystals in there. And then when the whole thing turns to ice, then the density goes way up again. All right, but what you got there is kind of slush with some ice crystals. So that change starts to occur about 4 degrees. That is the point where the volume is the smallest. It's where water has the most density. No ice crystals yet. Okay, so this is that same graph but turned around so that you can see how water is most dense at 4 degrees. So the density is the highest, the volume would be the lowest. Okay, so here's a problem, well, not from your book, but from a worksheet that goes with your book. And the idea is you've got some bottles of water here, and you're watching to see what happens to the level. So there's a chemistry bottle with a long, thin neck. And so the idea is that at 0 degrees, there's a lot of slush in here. And then at 1 degree, there's a little bit less. So if there's less slush, fewer ice crystals, then the volume starts to go down. So the volume starts here, and now it's gone down a bit. And what you're supposed to do, or what we're supposed to do, is think, okay, well, what's going to happen over time as you keep cooling this down? I'm sorry, warming it up or warming it up. And so as it warms up, it melts more of those crystals. So that actually makes it less slushy. And you melt some more, and you melt some more. And finally at 4 degrees. And at 4 degrees, there are no ice crystals left. So at that point, it just starts to expand like a normal material as it heats up. So at 4 degrees, it's the lowest volume, greatest density. Okay, so that's why, and then the water will start to expand again. And so that's what's special about 4 degrees. Now, this does affect our planet, of course, as everything does. So what happens in a pond as winter approaches? Okay, so you've got a pond, and it's air temperature, 20 degrees, maybe a little higher if it's a hot summer, maybe a little cooler. And what happens is that cool breezes start to blow, right? And as they do, they're going to take away heat energy. So heat starts to leave the pond. And the air temperature gets colder and colder, and more heat energy starts to leave the pond. Well, that heat energy is leaving the water, which is at the top. So that water starts to cool down. When it cools down, it gets more dense. And so it starts to drop down to the bottom of the pond. And so the water's dropping down, and then that pushes up warmer water. And this kind of circulation is called convection. And we'll talk about that in future chapters. So the water is circulating with cold water going down, warmer water going up. And eventually what happens is that the water has lost so much heat energy that the water that goes down is now 4 degrees. So the water is now 4 degrees, and it goes down to the bottom, and then it stays there. It's the most dense water can get, so it sinks to the bottom of the pond. Okay, but circulation keeps going above that. And more water reaches 4 degrees, And so it fills up the bottom of the pond, and more water reaches 4 degrees and drops to the bottom of the pond. And eventually, basically, your pond is filled with 4-degree water. Now, what happens is that the water that's left, the 4-degree water, if that fills the pond, then it will start to lose the last of the heat energy, and it will finally become 0 degrees Celsius. So the water at the top of the pond will be 0. Now, when it reaches 0, then you start to form ice on the pond. So the ice starts to form. So you get a layer of ice. Now, the thing is, when you get a layer of ice, well, ice is a good insulator. So what happens is you start to keep heat energy from leaving the pond. Whoops, that wasn't supposed to do that. Supposed to do that. So the heat energy stops leaving the pond, and then you put on more ice because it's still getting colder. And with every layer of ice that you put on, then it acts as an insulator, and the heat energy stops flowing eventually. And the pond is basically capped off, and it can't lose any more energy. So what happens? That's really important for life, because we can have animals that can swim around like fish, and they can swim around in the water, in the 4-degree water, and they're fine, okay? And we can still have plants growing, okay, underneath the water. And so life goes on under the capped ice. So anyway, so this is important, because if the water actually reached 0 degrees all the way down, then animals would freeze. And when an animal freezes, its cells burst because ice crystals form in the cells. And so most animals would die. Now, some animals are adapted. They can be frozen, like some frogs and stuff, and then thaw out. But most animals and plants don't have the antifreeze type stuff in their system that frogs do. And so their cells just burst. So anyway, so it is really important, that 4-degree lowest density, because that allows our ponds to still retain life even in the winter. So lakes freeze from the top down. What would happen if ice sank? So you can imagine, if ice sank to the bottom, that over the winter, let's say if this suddenly changed this next winter, slowly even Lake Michigan would freeze to the bottom. And then during the summer, you would probably only melt the top layers, right? So you would have a little bit of water, but down below it would be ice. So that would be bad normally for life as we know it. Okay, so that's the end of this chapter. And so that's the end of chapter 15. All right, see ya.